In the last web lectures, we learned a lot about the energetics of chemical reactions in general. What kinds of things make chemical reactions exergonic versus endergonic. We learned about how endergonic reactions can be coupled to exergonic reactions to make them proceed using the energy source of the exergonic reaction. And we also learned a lot about metabolic pathways and how they're facilitated by enzymes at every step of the way. So in the next several web lectures, we're going to put all of that information to use. And in this one, we're going to specifically be talking in particular about catabolic pathways, the breaking down of large macromolecules in exergonic reactions to produce energy that can be used by organisms. So the first part of this, we're going to think about these reactions and how this energy is transformed as it goes through all of them up through glycolysis, and we'll pick up in the next web lecture with the next couple of steps in cellular respiration. So let's just start with a general overview of cellular respiration. What is it all about? What is cellular respiration? So we know that life requires energy and that most of the work that's done in cells is directly fueled by ATP. And we saw in previous lectures and previous units that the work that the cell does includes all kinds of things such as these anabolic pathways, assembling large macromolecules from small monomer subunits, membrane transport, so moving materials across membrane to have a regulated environment within the cell, moving different parts of the cell, and also reproducing requires cellular energy. So metabolic pathways harvest energy from high energy molecules such as glucose. And so glucose contains a lot of energy, but we can't just burn all that energy in one explosive reaction. We need to do it in a very controlled way and actually harvest that energy so that it's not simply lost as heat. So the energy released is used to add a phosphate group to ADP to make ATP. That is the end game in all of this. This is the goal that we're moving toward in both this web lecture and the next one. So ATP has to be continually regenerated. So cells generally contain only enough ATP to sustain about 30 seconds of cellular activities up to just a few minutes. And ATP is unstable. It's not something that can be stockpiled and stored very easily. And so cells need to be making this all the time. And the larger macromolecules are basically where that energy is stored until the cells use it to make ATP. So plants produce glucose during photosynthesis, and then other organisms are going to obtain their energy source from food, ultimately in the form of glucose. Energy is going to flow into an ecosystem as sunlight and leave as heat. So remember that energy is this one-way street. It's going to be transformed into different forms, but ultimately it's going to come in as light energy from the sun and leave as heat. And the matter that make up organisms is going to be recycled, so all of these atoms. So we need to think about how energy flows through systems and then how those atoms are reused, how they're transformed to be used and reused by the cells. So the process of photosynthesis generates molecular oxygen, actually as a byproduct, as we'll see when we get to photosynthesis, and also organic molecules. So it does what we call fixing the carbon from carbon dioxide. It takes that carbon and converts it into larger organic molecules. And these are the raw materials that are used in cellular respiration. So we get organic molecules such as carbohydrates plus oxygen coming from photosynthesis being used by cellular respiration, and then cellular respiration is going to convert those materials to carbon dioxide and water, which are the raw materials for photosynthesis. So this is how these atoms are recycled ultimately. So cells use chemical energy stored in organic molecules to generate ATP, which is going to power the work. So that's going to be the output, and eventually that work is going to result in the release of heat. So given this cycle, it seems like it all starts with photosynthesis, and it might make sense to actually study photosynthesis before cellular respiration in some senses, because it seems like it's the beginning of this process. But actually the way we're doing this reflects the evolutionary history of these processes. So if we look again at this circular timeline of the history of the Earth, we get the beginning of life here about 4 billion years ago, but we don't get the first photosynthetic organisms until about 3.5 billion years ago. So what that means is that for 500 million years, there was life on Earth, but no photosynthesis. So this cycle of photosynthesis feeding into cellular respiration, and then the products of cellular respiration being what fuels photosynthesis, actually didn't even come about until about 500 million years after life began. So where did that energy come from before photosynthesis? So the earliest organisms were what we call chemoautotrophs. So that means that they gained energy from chemical reactions using inorganic chemicals and were able to fix carbon from carbon dioxide to construct organic molecules using that energy. And so these metabolic pathways that we're going to be talking about, these cellular respiration pathways, actually predate photosynthesis, and they're incredibly ancient, going back to the earliest forms of life, because remember that we said that these metabolic pathways, this transformation of energy, is on that list of things that all living things do. Everything, if it's going to be considered alive, has to have these metabolic pathways to transform energy. And so even currently, we still have microorganisms that do this trick of being a chemoautotroph. And so an example is that there are currently bacteria that gain energy by oxidizing iron 3 oxide to iron 2 hydroxide. Don't worry too much about the details of that. You'll learn about it in general chemistry. But these are basically anaerobic processes that do not use any sunlight as a source of energy. And there are other examples out there too, where other sources of energy are used as a source of energy for cellular activities. So now let's start to think about these catabolic pathways and how they're going to work. Catabolic pathways, remember, are these pathways that release stored energy in exergonic reactions by breaking down complex molecules. And this is going to be an energy releasing reaction. And the major way that they do this is by the transfer of electrons from one molecule to another in these very highly controlled, highly regulated pathways. So we have 3 major categories of cellular respiration we're going to look at over this whole unit, this whole chapter. One is fermentation. We're actually going to come back to that at the very end. This is a partial degradation of sugars that occurs without the use of oxygen. So it's not going to quite get all of the energy out that's contained in those sugar molecules, but it is a useful source of energy. We're going to look at aerobic respiration, which consumes organic molecules and molecular oxygen, yielding ATP. And this is also possible to get ATP in anaerobic conditions without using molecular oxygen. And these pathways are going to be similar to aerobic respiration, but they'll bypass the parts of the process that use oxygen. And just as a reminder, we're going to focus here on the breakdown of the sugar glucose because it's fairly straightforward and well studied, but all kinds of macromolecules can be used as a source of energy. Carbohydrates, fats, proteins are all broken down by cells and used for energy. And although we're not going to study this in any detail here, it's also useful to really think about the very close relationship between these catabolic pathways and anabolic pathways. So keep in your mind that these catabolic pathways are not just providing energy, but they're also providing raw materials for the construction of new macromolecules. And these materials are going to be pulled off from different points in this whole process of cellular respiration. Don't worry about the details yet. We're going to go through all of this. But lots of these byproducts of cellular respiration are going to be grabbed by these anabolic pathways and used to construct new biological materials. So I mentioned that much of this energy harnessing is going to happen through the transfer of energy by way of electrons. So now let's think about the reactions that make that possible. These reactions are called reduction-oxidation reactions, usually just abbreviated as redox reactions. And these are chemical reactions that involve some kind of transfer of electrons. So oxidation is the loss of one or more electrons, and reduction is the gain of one or more electrons. So it seems a little counterintuitive to think of reduction as being a gain, but think of it in terms of the charge that's going to be involved in that transfer of electrons. The transfer of electrons is going to make the charge on that molecule more negative, and so it's reducing the charge on that molecule. Because this involves both an electron donor and an electron receiver, these always have to occur together concurrently. And these reactions represent another energetic coupling of an exergonic and an endergonic reaction. And we think of these in terms of two half reactions. The oxidation part of it is exergonic, it's energy releasing, and reduction is endergonic, it's energy absorbing. So during a redox reaction, electrons can be completely transferred from one atom to another, or if they simply shift their position in covalent bonds because of changes in the relationship between the two atoms and their electronegativity. If they switch from a nonpolar covalent bond to a polar covalent bond, one of those atoms has gotten a greater share of those electrons, and we still consider this reduction, when an atom, through the course of the reaction, gets a greater share of shared electrons. So here's a very simple example of an oxidation-reduction reaction, just the ionization of sodium and chlorine. So sodium, remember, it just has that single electron in its valence shell. It's going to very easily give that electron up, so that it has a completed valence shell full of electrons. And so we say that sodium becomes oxidized, it loses its electron and gives it over to chlorine. So chlorine is going to accept that electron, it's going to become reduced. So remember, it's reduced, its charge decreases to a negative charge. If we think about the energy states of the electrons in this process, when an electron is transferred from a less electronegative atom to a more electronegative atom, that electron is in a lower energy state. Why? Because it's gone from an atom that has less affinity for that electron to an atom with more affinity for that electron. Because it has higher affinity for the electron, it's going to hold it closer to its nucleus, and electrons are in their most stable state the closer they can be to the nucleus with the protons. So atoms that are reduced are in a lower energy state than atoms that are in their oxidized state. So the electron donor we refer to as the reducing agent. So in this case, sodium is the electron donor. This is the reducing agent that's going to reduce chlorine to chloride. The electron receptor we call the oxidizing agent. It is going to oxidize sodium into the positively charged sodium ion by accepting that electron. So now let's look at the more complicated situation where there's just a change in the covalent bonding from a nonpolar to a polar state. So in this case, we're looking at the oxidation of glucose by reacting with oxygen to form carbon dioxide and water. So we can say that carbon is oxidized because it loses some of its share of the electrons. So here in the glucose molecule, where it's got bonds to hydrogen and other carbons, all of these electrons that are part of these nonpolar covalent bonds are equally shared. But now when we go and transform that to carbon dioxide, now those electrons are being pulled away from the carbon. So the carbon has less share in those shared electrons. It has lost some electron influence. So we say that the carbon is oxidized. Also, some of these hydrogens that are equally sharing electrons are oxidized when they form water because those electrons are being pulled away from them and toward oxygen. We can say that oxygen is reduced, conversely, because it's getting a greater share of those shared electrons. So the oxygen in the molecular oxygen, remember this is a nonpolar covalent bond. You've got two oxygens that are equally electronegative. They're going to share those electrons equally. As the oxygen goes toward carbon dioxide and water, the oxygen is going to get a greater share of those shared electrons. So now we can say that oxygen is reduced. The atom that is oxidized, we call it the reducing agent. It's carbon that, when it combines with oxygen, that allows oxygen to be reduced. So carbon is the reducing agent, and oxygen is the oxidizing agent. That's very easy to remember. Oxygen, being one of the most electronegative atoms, is the strongest oxidizing agent there is. So another way to understand these redox reactions is to understand that electrons are transferred from an electron donor to an electron acceptor, but they usually come packaged together with a proton as an actual hydrogen atom. And so a lot of times what you'll see in these redox reactions is H's being added to the to whatever the molecule is that's being reduced, because those H's are coming along with electrons. And so we'll often see that oxidation often removes H's. And this is really important to understand because two of the big players you're going to be seeing in these redox reactions involved in cellular respiration, basically the change that you see in their chemical formula is basically a change in addition of these H's when they become reduced. So for example, flavin-adenine dinucleotide, which we'll just refer to as FAD, is going to accept 2 electrons plus 2 protons to form FADH2. And nicotinamide adenine dinucleotide, we will just call that NAD+, so this is a positively charged molecule, accepts 2 electrons plus 1 proton to form NADH when it becomes reduced. So remember that when you see the addition of these H's, there are electrons coming along with them. And so this one is easy to remember that it's reduced because it's going from a positive charge to no charge, so that overall charge has been reduced. Not quite so easy to see with this one because it comes with both 2 protons and 2 electrons. So these electron carriers are going to readily donate their electrons to other molecules. They're going to be able to accept those electrons because they're a little bit more electronegative than the organic molecules that they are taking the electrons from, but they're going to readily hand those over to even more electronegative molecules down the road. So now let's start to take a closer look at the oxidation of these organic fuel molecules during cellular respiration. So we know that these are exergonic reactions. Burning glucose in the presence of oxygen is going to give off carbon dioxide and water. Somehow this got misaligned, but there's a glucose, there's oxygen, carbon dioxide, and water, and it's also going to release some heat and light. So the oxygen atoms are reduced to form water. In cells, glucose is oxidized through a very long series of very carefully controlled redox reactions, which we will be working our way through as we go here. So the released free energy is used to synthesize ATP. We'll talk in detail about how that happens. And in all, this whole process of going from a glucose molecule all the way down to carbon dioxide and water is what we call cellular respiration, regardless of whether that happens in the presence of oxygen or not. So as we've been mentioning, this energy harvest is going to happen in a series of small steps. And the big player in this is going to be NAD+, which is going to be reduced, and something we call the electron transport chain that's going to carry out this series of redox reactions and transfer those electrons down to lower and lower and lower energy states harnessing that energy as we go along. So in cellular respiration, glucose and other molecules are broken down in this large series of steps. So electrons from organic compounds are usually first transferred to NAD+, which is a coenzyme. So here is the reaction that undergoes. So here we have some sort of biological molecule with some hydrogen atoms attached to it, protons and electrons, that are going to be transferred over to NAD+, 2 electrons plus 1 proton. The other proton is going to be released into the environment to form the biological material without those hydrogens, plus NADH, the reduced form of NAD+. So as an electron acceptor, NAD+ functions as an oxidizing agent during cellular respiration. So NAD+ is our oxidizing agent. It becomes reduced. Okay, our biological molecule becomes oxidized. So each of these NADH molecules, the reduced form, represents a little chunk of stored energy that's later going to be used to synthesize ADP down the road at the very end of this process. So here we can see the oxidized and reduced forms. Before it accepts that hydrogen ion and the 2 electrons, we've got a carbon in the ring with a double bond. Here to the next carbon with just 1 hydrogen bonded. The reduced form adds that hydrogen, eliminates that double bond, and now is an uncharged molecule with 2 additional electrons that it didn't have before. Eventually, NADH is going to pass these electrons down to what we call an electron transport chain, a series of increasingly electronegative molecules that are going to accept those electrons and become alternately oxidized and reduced as they pass those electrons along. Again, we'll look at this in a lot more detail. This is just to give you an overview of how this works. So if we were to just burn these molecules in one kind of explosive step, basically we're going to have a huge release of energy that's just going to be dissipated as heat and light. Instead of doing an uncontrolled reaction where we just burn it all up, the electron transport chain passes electrons in this series of steps. In each of these smaller steps, we can actually grab that energy that's released and use it to create molecules of ATP. So ultimately, the electron acceptor is going to be molecular oxygen, and oxygen being the most electronegative of all of these molecules in the electron transport chain is going to be grabbing these electrons, causing this element to be oxidized. The oxidized form of that is going to just grab electrons from the one before it. So now this is reduced and this is oxidized, and oxygen is just going to pull these electrons down the electron transport chain like gravity can pull something down a staircase in little small steps. And then ultimately the end game is going to be regenerating ATP, because remember there's all of this ADP and inorganic phosphate around from the use of ATP to power all the work that the cell does, and so all this energy is going to be used for regenerating ATP. So what actually happens in this process? So cellular respiration is a set of 3 processes. So the first process is glycolysis. We're going to go into detail on that during this web lecture, and this is the process in which a 6-carbon glucose monomer is broken down into 2 3-carbon pyruvate molecules. The next part of the process is the citric acid cycle. The pyruvate, before it can enter the citric acid cycle, is converted to a molecule called acetyl-CoA. And the acetyl-CoA is going to be oxidized to carbon dioxide during this part of the process. And then finally, it's going to go through this process of oxidative phosphorylation by using the electron transport chain, which is going to be generating the energy to power this oxidative phosphorylation. So electrons are going to move through a transport chain, and their energy is going to be used to set up a proton gradient, which is then going to be used to power the synthesis of ATP. Again, this is just an overview. We're going to go into much more detail on this, so don't worry if this sounds a little bit vague at this point. So this last step, the oxidative phosphorylation, is the process that generates the bulk of the ATP. This is where most of it is happening. And because it's powered by this fall in energy state of these electrons as they go through the electron transport chain. So that's where most of this energy is released, and that's where most of the ATP is going to be generated. So a smaller amount of ATP is formed in glycolysis and in the citric acid cycle by what we call substrate level phosphorylation. So the difference between substrate level phosphorylation and oxidative phosphorylation is basically that the phosphate group in substrate level phosphorylation is going to be transferred directly from another molecule to ADP to form ATP. That's the substrate. Okay. In oxidative phosphorylation, basically inorganic phosphate that is present in the cell due to the breakdown of ATP during previous cellular processes, the inorganic phosphate that's just there is going to be directly combined with an ADP rather than that phosphate group being transferred from another molecule. So oxidative phosphorylation versus substrate level phosphorylation. Oxidative phosphorylation is going to generate a lot more ATP. So for each molecule of glucose degraded to CO2 in water by respiration, in the presence of oxygen, if we're using this oxidative phosphorylation, the cell makes up to about 32 molecules of ATP. So we can think of this as using money as an analogy. So glucose is like a large denomination bill. It's got a lot of value in it, but finding somebody who's going to actually accept that large denomination is not as easy as spending smaller bills. So ATP is like a large number of smaller denomination bills of equivalent value. They can be spent more easily. So the process of cellular respiration basically is making change, right? So it cashes in this large denomination of energy for the small change of lots and lots of these molecules of ATP. So now we're going to start to go through each of these 3 steps of cellular respiration. And for each of these steps, what you really want to be asking yourself and thinking about and keeping track of are the following questions. What goes into this part of the process? What are the inputs? What are the outputs? What comes out at the end? So to some extent, it's helpful to kind of think of these processes as a black box where things come in, something happens inside, and other things come out. You need to know a little bit more about the details of how that happens, but in general, that's a good way to kind of start to get your mind around it. So what happens to the energy that's released? How is energy transformed during this part of the process? In what physical location does each step occur? Where is this happening? How did it get there? And then also, how is it regulated? How is this process controlled? Here's a good overview of this whole process with all of the different inputs, not in their proper quantities, but just an overview. The outputs, so the out arrows are what's coming out. And for glycolysis, processing pyruvate into acetyl coenzyme A, acetyl-CoA, citric acid cycle, and then finally oxidative phosphorylation through the electron transport chain. So using this figure and then filling out these inputs and outputs and energy changes is a good way to organize this whole process. So let's begin now with glycolysis. So glycolysis is going to harvest chemical energy by oxidizing glucose to pyruvate. So this one 6-carbon sugar monomer to 2 3-carbon sugar monomers. So glycolysis is a series of 10 chemical reactions, and this is going to occur in the cytosol, so outside of the mitochondria. And the 3 key points to remember are: first, glycolysis starts out by using energy. So 2 ATP are going to be used in something that we call the energy investment phase. So these are reactions 1 through 5. Second, after this energy investment phase, we have an energy payoff phase. And during this energy payoff phase, reaction 6 to 10, this is where we're going to get energy stored in the form of NADH, and we're going to make some more ATP by substrate level phosphorylation. So we're going to have a net gain of ATP after this investment. So that's what we call it, the payoff phase. The net yield of all of this is going to be 2 NADH molecules for every molecule of glucose that goes in, a net gain of 2 ATP, and then you're going to have your 2 pyruvate molecules as products of this reaction. So another thing to notice is that oxygen, molecular oxygen, plays no part in this whatsoever. So glycolysis occurs whether oxygen is present or not. So we're going to get some gain of ATP even without using any oxygen. So now let's start to look at the reactions themselves. First thing, don't panic when you look at this. I do not expect you to memorize all of these reactants and products. I do not expect you to memorize the names of the enzymes that facilitate these reactions, but I do want you to notice some things about how these molecules are changing through this process. I do want you to understand where the ATP is used and for what, and where we end up gaining ATP and NADH in the end. So let me walk you through the things I want you to notice about these reactions. So in the first step, we're going to use an ATP right off the bat to phosphorylate the group on the 6th carbon. So we're going to phosphorylate this. What do we do? Anytime we phosphorylate something, we increase its energy state. We've put this into a higher energy state to power something else that's going to happen. In the second reaction, we're changing from a 6-carbon ring to a 5-carbon ring. So we've created an isomer, a structural isomer of the original ring. In this third step, we're using another ATP. We're going to phosphorylate another carbon group. In this case, it's going to be on the carbon number 1, the first carbon. And the other thing to notice is that at this point, we've created a ring that is nearly symmetrical. There are some differences in the positions of these hydroxyl groups, but otherwise we've got the same stuff on either side of this line of symmetry. So now that we've got this nice symmetrical ring, we're going to split it in half and have 2 3-carbon chains with the same molecules in them so that they're basically isomers of each other. So one isomer is G3P, glyceraldehyde 3-phosphate. The other isomer is dihydroxyacetone phosphate, DHAP. And in this 5th step, we're basically going to convert DHAP into G3P so that now we have 2 identical molecules that are going to go into the energy payoff phase. So here's the energy payoff phase. So we're starting now. We're only showing one of these 2 3-carbon chains, but remember that we have 2 of these since we converted the other isomer into another molecule of G3P. So all of this is multiplied by 2 from here on out. Okay, so again, just noticing what's changing in each of these reactions. So here we're going to have the reduction of 2 NAD plus to NADH, 1 for each of these G3P molecules. And then also this G3P is going to be further phosphorylated using inorganic phosphate from the environment. So now we've got 2 phosphate groups on our molecule. And now that we've got these highly activated, high energy phosphorylated molecules, we're going to take those phosphates and do substrate level phosphorylation, transfer those phosphate groups to ADP to create 2 molecules of ATP. So we still have 1 phosphate group left on there. Remember, this is 2 molecules of this, and it's just 1 for each of those. It's going to phosphorylate ADP. We still have the phosphate, and basically in the next step, we're going to transfer that phosphate to the central carbon. Then the next step is just a dehydration reaction, removing 2 hydrogens and an oxygen. I'm going to remove this hydroxyl group and this hydrogen to form this intermediate. And then finally, we're going to have 1 more round of substrate level phosphorylation. This phosphate group is going to come off of each of these 2 molecules. Remember, everything's doubled going through to get our 2 more ATP as that phosphate group is removed. And we end up in the end with 2 molecules of pyruvate. So let's look at the bookkeeping now. We've got the energy investment phase where we have a glucose going in. We're going to use 2 ATP and what's going to come out, 2 ADP and 2 inorganic phosphates. In the energy payoff phase, we're going to gain 4 ATP by substrate level phosphorylation. Remember, those phosphate groups are going to come from those carbon chains that were phosphorylated in this first step. And we're going to reduce 2 NAD plus into 2 NADH and gain 2 protons in the bargain, and end up in the end with 2 pyruvate plus 2 water molecules. Remember, we had that dehydration reaction, so there's some water coming off. So the net is that glucose is transformed to 2 pyruvate and 2 water molecules. 4 ATP are formed minus 2 ATP used. We've got a net gain of 2 ATPs. So the 2 NAD plus are going to be reduced to NADH, and 2 hydrogen ions are going to come off in the bargain. So now let's take a look at how this process is regulated. So glycolysis is going to be regulated and controlled by feedback inhibition. If there ends up being too much ATP in the environment, high levels of ATP, if it's not being used up fast enough, is going to inhibit the third enzyme in this pathway. Don't worry about memorizing this name, but phosphofructokinase is going to be an enzyme that has both an active site, an active binding site for ATP, because remember ATP is going to be a substrate that takes part in this reaction, right? This is one of the energy investment steps where ATP is broken down to ADP and molecule is phosphorylated. When during normal functioning, ATP is going to bind to the active site on phosphofructokinase and help to catalyze this third step of producing the fructose 1,6-biphosphate. But when there's too much ATP around, when it's accumulating, it's going to bind to a regulatory site, an allosteric regulatory site, that's going to inhibit this enzyme's activity. So if we look at what this looks like in a ribbon model, here we have the active site down here. We've got our sugar ring, our carbon ring here that's phosphorylated. We've got our 3 phosphate groups on the ATP that's here in the active site. But then there's this regulatory site that also binds ATP and will cause the activity of that enzyme to decrease and slow down the process. So now let's take a look at these 3 questions and just make sure that we've answered all of them before we move on to the next step in the process in the next web lecture. So same key questions. What goes in? So glucose is the input. What ultimately comes out? A net gain of 2 ATP, 2 NADH. So remember, this is where that energy is stored from that oxidation reduction reaction that's going to go on to power the production of ATP later on in the last stage of this process, and then 2 pyruvate molecules which are going to move on into the next stage of this reaction. So what happens to the energy that's released? So we're going to have some of it stored in these ATP molecules that are produced, and a lot of it stored in the NADH that's going to move on. Where does this occur? It occurs in the cytosol. Remember, this is outside the mitochondrion. And it's regulated, as we just saw, by feedback inhibition by ATP. We're going to leave this here for now. In the next web lecture, we're going to pick up right here where we left off with these 2 pyruvate molecules moving into the mitochondrion, 2 of them for every glucose, and going on into the citric acid cycle.